between taking care of people and trying to teach people responsibility. And some of you who have come through I was just talking to Caitlin about this yesterday. You know, I say it's really hard for some of our 107 students that may have taken 095 or 096 with us, or maybe even started in 090, because, you know, we sort of like nurture you along. And then boom, you get to 107 and life has changed, because 107 is a college algebra class, it's college credit. And a lot of students that take this, you're going to be going on to, you know, the big bad universities or private schools or whatever. So we've got to slowly start sort of in a way weaning you from some of these things. So by my doing this, I'm still kind of taking care of you a little bit, and that's okay. I don't mind. It's the beginning of the year. We're only in our second week. But please, if I ask you to do something, please do it, because I may not always do that, okay? Now, so we talk a lot about trying to prepare you for transfer. That's really one of our key things at this institution. So I can't stress to you how when you go to, say you go to UMass, if you're in the BAT program, or you go on to study environmental science, wherever you are, you're not going to be handed lecture notes. You're not going to be handed class videos. Okay, so I don't know if that's doing too much for you, but use it, make it available to yourself, and please use our resources. You know, we've got the studio. I see very few. I have to say that this is the first time I've had an 8:40 class and I don't see people in the studio. I'm used to walking in at like 10 of 8 o'clock, and I usually have 4 or 5 students in here, you know, and as I'm setting up, they're saying, I got a question on this and this. So please use it, because I want you to do well on Monday. Okay, I want you to do well on Monday's quiz. So that's a reminder about the quiz. I said you can use one of these little things, both sides, I don't care, for your quiz on Monday. These are on my door. If you happen to have little index cards like this, that's great. If you don't, stop by my door and you use a piece of paper, it can't be bigger than this. And I don't know what this is. What is this? 3.5 by 5, you think? Is that? Oh, here you go. 5 by 3. Okay, 5 by 3. So if you want to cut out your own little piece of paper, that's fine with me. Use recycled paper, that's even better, right? We're saving the planet or helping. So today your project's due, that goes in the folder. Today we're going to cover the second part of this topic, where we get to use 2 variables instead of 1. In section 1.3, class 5, you were supposed to be doing these problems with 1 variable, but some of these problems are easier to do with 2 variables. And so we're going to take a look today at systems of equations. We're going to do a real quick review of this. If you've taken math 096 or 106 recently, you would have seen this. So let's start us off by reading this, Tyler. Okay, so if you don't know, here's a system of linear equations in 2 variables. Both of these equations represent a line. Okay, if you solve each of these equations, this is called general form. If you solve this and put them in the y equals mx plus b, which is what you're more familiar with, you will see that one of those lines has a positive slope and one of those lines has a negative slope. So when we talk about solving a system of linear equations in 2 variables, it's going to look like this. And one of the ways you can solve the system is you could actually graph each line and look for where they intersect. Now, not all lines intersect. They might be parallel. But in this particular case, these 2 lines intersect. So the idea of the solution, the one solution in this case for this system, is an ordered pair. It's an x value and a y value. And it's this particular point right here, 4, -1. That is the common solution. So what that means is if you go back to the system, here's your system, x plus 2y equals 2. and x minus 2y equals 6. And we're saying that the point 4, -1 is the common solution because it lies on both. It's a point that both of those lines have in common. So since it's a solution, you should be able to go back and replace x with 4 and y with -1 and get a true statement. 4 plus -2 is 2. That's correct. And then it should also work for the bottom equation. 4 plus 2 is 6. That's correct. So one way to find solutions to these systems is to actually graph both lines and find where they intersect. That's kind of a pain, all right? So it's a pain because sometimes you could get really ugly solutions like this, 17/9 and -3/7, which are not easily going to be able to see from a graph. So we have two algebraic methods. I think probably some of you have heard these names before, substitution and addition. Now, some books call this elimination instead of addition. And I've actually seen another name for it. I'm trying to remember what it is. I can't remember off the top of my head. This is what your book calls it, addition. So let's take a look at both of these methods. All right, so here's our system. Here's our system right here. And our goal is to find a common solution. And remember, the common solution has two pieces. It's an x value and a y value. So you don't stop once you find x. You got to find both x and y because you're looking for a point, okay? So the substitution method is usually a lot of people's favorite way to do it. If you look at both of your equations and you see one of your variables with 1 as a coefficient, 1 multiplying it, then it's really easy to solve for that variable. So in our particular case right here, we notice that in that equation, we have 2x plus 1y is 1. So you rewrite it. And to rewrite it, you're going to say you're going to solve it for y. That's the language we use, solve for y, which means we just want to have y on the left side and nothing else. So how would I rewrite this equation so it's solved for y? What would it look like? Yep. 1 minus 2x, or y equals -2x plus 1. Both of them are the same. It doesn't matter how you write it. Okay. Now you know y's identity. Put it in parentheses and put it into your first equation. So your first equation is 3x plus 2 times y equals 4. And literally the word substitute is exactly what you're doing. You're going to substitute for the value of y. This says y is equal to 1 minus 2x. So where I see y, I'm going to replace it with an equivalent expression, 1 minus 2x. And now I have one equation with one unknown, and I can solve it. So I get 3x plus 2 minus 4x equals 4. That's -1x plus 2 equals 4. -1x equals 2. And I divide both sides by -1, and I get x equals -2. But you're not done, because you're looking for an ordered pair. You're looking for that point where they intersect. So you always go back to one of your original equations. Why? Why do you always go back to an original equation? Why don't I just go back into one of these ones I've already worked with to find y? Anybody know why they say always go back to the original? Okay, so the reason is, let's suppose you made a mistake here when you solve for y, and you put it in here and you get a value for x. If you go back in here and put the x value in and get y, it's going to work for that particular equation, but it won't work for your first one. If you make any mistakes along the way, it's not going to reflect the mistake. Okay, so you always want to go back to one of these original equations that you didn't try to rewrite or manipulate. So let's go back to the 2x plus y. We know what x is, and now we're going to solve for y. So we have 2x plus y equals 1. That's one of my original equations. Okay. So I could have picked either one. I don't really have a favorite here. And I just said x is equal to -2. Do you have your notes, Kenneth? I didn't give them to you? I thought I handed it to you. You were sharing, wait a minute. Did you need a packet too?
Yeah, but you said you only had the one.
Well, I had my one for my own notes. Okay. So let's see. So you say, okay, x is -2. So you come up here, you throw in -2, and you get -4 plus y equals 1. And now you solve for y equals 5. So now you have your point of intersection. And if you're really one of these people who are like, I don't trust that, then you could go into your other equation, throw that solution in. 3 times -2 is -6, plus 2 times 5 is 10, -6 and 10 is 4. Now you feel pretty confident everything's okay. Any questions on how you use substitution to solve a system? Anything? So a lot of times you get these systems and it's not set up where one of these variables has a 1 in front, and then you get involved with all these fractions and it can get really ugly. So there's another method that you can use to solve these. And so let's take a look at that. I'm just going to put this on the other page so we have a little space. Or I need a little more space than you do because I write so big. Let me just take that, grab that. Okay, so here's our original system, and now we're going to look at the addition method. And the addition method does exactly what it says. It takes your original system, and it says, well, if all of this is equal, then if I add the left side and I add the right side, I should get another equal statement. So the problem is if I add this left side, just as it is right now, I get 5x plus 3y equals 5. And there's no way I can solve that because I have just one equation with 2 variables. Can't solve it. So you say, okay, so what's the big deal with this addition method? Well, the big deal with the addition method is the addition method is really helpful if you can somehow rewrite these equations so that when you add the left side, one of these variables is eliminated. That's why some people call it the elimination method. So the key here is to get the coefficients. That's these guys right here. These are called coefficients. Coefficients. So you want to create coefficients that are opposite of each other. So when you add them, you get 0. So you have lots of choices here, but you want to do as little work as possible. That's kind of a human nature thing, right? So if I were looking at this and I wanted to get rid of x, I'd have to multiply the top equation through by a number and the bottom one because I don't have a 1 here. Whereas if I think about getting rid of y, all I have to do to make this go to 0 is have what kind of number out here to make this become -2. So that means I just have to multiply one equation by a number, and that number is going to be all the way across -2. So now I rewrite my system. My original equation was 3x plus 2y equals 4. And now my second equation, I've multiplied both sides by -2, so I haven't changed it. I have a right to do that. So I get this now. So there's my second equation. I've rewritten it by multiplying it by -2. Now when I add everything on the left and everything on the right, I eliminate one of my variables, right? Because this goes to 0. Okay, that just goes to 0 when I add that. 3x minus 4x is -1x equals 4 minus 2 is 2. So x equals -2. We already knew what the answer was. So this just verifies that -2 was correct. And now again, you go back to one of your original equations, throw in the -2, and solve for y. So -6 plus 2y equals 4, 2y equals 10, y is 5. And then you represent your solution as an ordered pair and you put a circle around it or a box. Okay. So is this new to anybody in class? this idea of solving a system? If it is, I can give you a little more additional practice either in the studio or in my office if you want. I guess I'm assuming that you've seen this before, linear equation solving systems. Let's put it to practice with these word problems.
For graphing that, you would obviously have to like solve for y.
Yeah, for graphing, well, not.
Solve for x2.
All right, if you were to graph this, let me show you what you would do real quick since that question came up. Usually, most of us, we can all be like a little quiet here. If I say, what's the equation for a line? I always hear y equals mx plus b. So if you rewrite this where you solve for y, this equation would look like this, minus 2x plus 1. We just, 1 minus 2x. So that's going to be an equation. That's going to be a line that has a y-intercept at 0, 1. And let me clear this all out. This is from our work the other day. So if we graph that first line, we get y equals negative 2x plus 1. So we should, in our mind, be visualizing a line with negative slope, negative 2, and it goes through our y-axis when x is 0, y is 1, because this is our y-intercept. Okay, so that's that equation. So we've rewritten that. This top equation, 3x plus 2y equals 4, you want to solve that for y, so you get 2y equals negative 3x plus 4. And now you divide both sides by 2 and you get y equals negative 3/2 x, and 4 divided by 2 is 2. So then you graph that one. So negative 3/2 is negative 1.5. So we have negative 1.5x, what is it, plus 2. All right, now I'm just going to try my standard window to see if I can find where they intersect. So we'll just try zoom 6, and let's see if we can see where they intersect. Yep. So we know it's right there. So where do we go to find the intersection point? We go up here to the calc button. Second trace is our calc. We go down and say, where do they intersect? Hit intersect. And then you go 1, 2, 3. Cool, you don't have to mess around at all. And there's the intersection point, negative 2, 5. Okay, Paul? All right. So let's get a little picture of that since we did it. Put it right, put it right in here. I know I got to get that camera up first. Where's the camera? There it is. All right. So they changed the system on me over the summer and it always disappears. All right, so there's the same intersection point of those two lines. Good question, thanks. Okay, anything else? All right, so here's an investment problem. Does this look familiar to you at all? I don't have a packet. Okay.
It was on the video, right?
It was on the video, right. And I said I would put it in, instead of putting it into class 5, I would put it into class 6. Now, class 5 is from section 1.3, so they do all of these with just one variable. And you can do this problem with one variable. I want to show you how you use 2. Okay, so someone want to read this for us? Tony, you want to read that?
Selection fund has 10,000. We invest in 2 funds, one low risk, high risk. Low risk fund, we expect a return of 4% annually. A high risk fund will get 8%. We want to have an expected return of $550. As little money in a high risk fund as possible. How much should we invest?
Okay, and then the fact is what I just said, that we solve, and if you read section 1.3, they do a problem like this in one variable, okay? And they have an example in the book. So we're going to look at how to do this in 2. Now, I try to go around to some of the tables and talk to you about sort of the musts that if you really want to conquer, and I don't call these word problems, I call them story opportunities. If you really want to conquer these, there's a series of steps, and I know it just sounds like I'm being harping on you as a math teacher, but it's a critical thing that happens up here, that defining what each variable means in each variable expression in terms of a numerical quantity is key. So notice how I've set up this table. If you look at amount invested, that represents a number to you, right? Doesn't the language, it doesn't say it's the low risk or the high risk. That's a qualitative thing. You need to see these variables as numbers. So I'm going to keep my table set up here, but I'm also going to show you how you would write it, how you would define or describe each variable expression in words. So we've got two things going on here. And one of the keys for those of you who always have trouble starting is to look at either the question at the end or what they tell you to find. So it says, how much should we invest in each fund? So you've got to define two quantities, either in one variable or two. So let's do two because we're in this section. So we're going to say let X equal, and again, it's got to be described as a number. And if you've had Sandy Goki, you got lots of training in this with Sandy. The amount of money invested in dollars. You always put your unit. And Y is the amount of money invested. Well, first of all, the amount of money invested in dollars in the low risk fund. So notice I'm not just calling it low risk. It's not a qualitative thing. It's a number. Now you get to be lazy and just go like this with your little, and then you say in high risk. So those are two of the things they're asking us to find. So if you create this little table, and some students really like it, it provides a structure, and you put the appropriate heading in the first column. The lower rate you're calling X, the amount invested at the lower rate or the low risk, if you want to just keep it so it looks just like it does upstairs in the description, and the amount invested in the high risk is Y. Now, when you solve one of these story opportunities, you've got to find what is equal to what. I know that sounds silly, but I read this a long time ago in an article about teaching mathematics, and I'm like, yeah, if you can't say what's equal to what, you're never going to be able to come up with an equation. So in words, can anybody tell me anything about what is equal to what here in terms of X and Y? What's equal to what? You can say it in words or you can use the actual variables. Eddie? Right, so if you go back here to this very first sentence, where's my highlighter? It doesn't want to give me my highlighter, right here. Oops, that's not very pretty. Where's my highlighter? Come on. How about over here? There we go. So if you come right back here, this $10,000 represents something. It's the amount you invested in each fund. It's the total amount. So you could say that in words, or you could say it in algebra. If you can, if you can say it in words, or if you understand it in words, then you just rewrite it in terms of the algebra. If you see these as dollar amounts, it's really helpful. That's one of the what equals what's. If you're going to solve one of these story opportunities with two variables, how many equations you got to come up with? Two. So here's one of them, because you're going to create a system. That's why I just spent the time showing you how to solve a system. So what equals what? Well, I know that the original amounts equals 10,000. There's something else going on in this problem. What else is going on in this problem besides just the amounts of money? The interest amount. And the interest amount is a small piece, really small, of the amount of money you put in. Okay, we've got in the low risk fund, we've got 4% annually, and in the high risk fund, we have 8% annually. There's nothing down in this box. Oh, let me show you what I can do. What can I put at the bottom of this first column here with the amount invested? What goes in here? 10,000, right. So if you fill in your chart and you go like this, here's your first equation. Okay, now when you multiply straight across here and you get this expression, that expression, this is a really small number. Well, it depends on how big X is, but it's still really small in comparison to X. What does this represent in words? The 0.04X, I'm going to put it right beside this one, 0.04X. Could someone tell me how I would define that in terms of words? 0.04X? What would be the unit on 0.04X? Can anybody figure out the unit? It's dollars, because 4% has no units attached to it. Percentages are unitless. So what dollar amount does that represent? Bob? Right, so it's the amount of interest, right? Amount of interest, right, earned on how many dollars? Not in this particular case. How many dollars have I invested if you look at that expression? X dollars, on X dollars. That's the hardest part, believe me. That's the hardest part of this right now, what we just wrote. Really understanding that that little variable expression is the amount of interest on X dollars. So what does 0.08y represent? When I put that in here, what does that represent? Can you tell me in words? Right, amount of interest. Now look, once you write this clearly, I'm trying to help you be like the best story opportunists in the world. Once you write this, amount of interest earned on my low risk investment, X dollars, amount of interest earned on my high risk, you know what it equals, don't you? What does it equal? Go back to your problem. The minute you say it in words, you know it's got to equal that other number right there, the 550. So 0.04x, which is the amount of interest on your low risk investment, and 0.08y equals 550. So now you can put these two together. This is your second what equals what. So when you put them together, it's called a system of linear equations in two variables. And you have a choice here as to how to solve it. You can use either addition, or you can use substitution. And the substitution idea is what you were taught in section 1.3. They don't introduce y, but they solve for y. So if we solve this top equation for y is going to equal your total amount invested, take away the amount of money invested in your low risk fund. That has to be what's left over. That's what 10,000 minus x means. If x was $6,000, then the amount put in y would be 10,000 minus x. Now, the only mistake students make when they represent it in terms of one variable like this, without doing this equation, that's why I kind of like solving these with two variables instead of one like they do in section 1.3, because a lot of times when you're in section 1.3, what I see here a lot is x minus 10,000. You know, and that's going to give you a negative number because this is your total amount. So you can't say x minus 10,000 because that will give you a negative number. So now you're really all set to go. Do you see how to use substitution here? Someone want to let me know how you would substitute? What you would do next? How about someone from table 2 back there? Sandra, Lana, Sam, Lissa, Sarah? Anybody? Well, which one, Cassandra? Because I got that from second, right? Okay. Because I can't put it back into the equation I just did, all right? I would get 10,000 equals 10,000. Okay. So now I go to my second equation and I substitute for y. And once I do that, I'm really a happy camper because I now have one equation with one variable and I can solve for x. Now you all have calculators, so you're probably not that concerned about changing these decimals to whole numbers. So let's just work with that since I know you all have calculators. I would go ahead and multiply everything by 100 because I like working with 4 and 8 better. But you know, you don't care anymore because you have these calculators. So what's 8% of 10,000? 800. Does that make sense to everybody? Okay, 800 minus 0.08x equals 550. I combine my two like terms here. 0.04x minus 0.08x is negative 0.04x plus 800 equals 550. Now I subtract 800 from both sides. And let's see, what do I get? Negative 0.04x, and what's 550 minus 800? Negative 250, and now I divide both sides by negative 400ths. And anybody got that from their calculator? What? 6,250. So let's see if this now works. Have I solved my word problem, by the way, my story opportunity? No, because it asked me how much was invested in both. So I come back here and I say X is equal to 6,250. I don't have to put the dollars on there, it's just a number. I understand X is in terms of dollars. And now to get Y, what do? 10,000, my total, take away 6,250 is 3,750. Okay. And then to really check it out, you multiply this by 4% and you multiply that by 8% and hopefully you get your 550. Did I do everything correct? Did anybody check me on this? You did, Paul? Okay.
Maybe it's just my app. I do final part or whatever. Increase, not like taking a whole bunch.
I understand 1.04 would represent the amount. So if I asked you how much money would I have at the end, totally invested, Mason, that would be the 1.04x and the 1.08y. But what they give you is the total amount of just the interest. So that's why you have to use these two, just the pieces. Okay? If I had a sentence there that said, after investing 8% in the high risk and 4%, I was going to answer your question if you give me a second. If Mason, if this had said I end up with 10,550, if that's the equation you want to write and you have 1.04x and 1.08y, absolutely fine. I have no problem with that, okay? But I don't want to introduce that as another way because I want people just to understand this particular way. But I got where you're coming from and I absolutely agree it's okay. All right? All right, so the last thing we have to cover so you can do your homework is this idea of break-even analysis. And who hasn't read today? Let's see. I haven't asked anyone from table 1 to read. Anybody over there feel comfortable reading that? Break-even analysis? Okay, Chris?
So you have to sell enough units so that full revenue. This occurs to say that the sale of the product break even. Take a look at the following higher knowledge.
Okay, so how many people are in here in one of our business programs? Everybody there, Sam and a couple people over here. Have you looked at break-even points in, say, economics at all? You haven't looked at in any business application? No? Okay, well, when you go on to take Math 151 next semester in the fall, you'll do this a lot with the applied calculus. How about supply and demand? Have you looked at that idea? When supply and demand are equal? It's the same idea. You're finding a point where your supply is equal to your demand. Here, we're trying to find a point where our revenue and our costs are equal. That's where we break even. Once we get beyond that, we start pulling in the dough, right? Good old capitalism at its best, right? Before that, we're in the hole. We haven't made any money. So when our revenue equals our cost, so R is going to represent the amount of revenue in dollars, and C is the amount of cost in dollars. When those two things are equal, that's what we call our break-even point. I'm surprised. Maybe they're using something else in business these days, but not that I know of. Okay, well, let's see. All right. So this is an example from our text. Now, I just want to caution you. If you read the textbook, because it's chapter 5, you're going to see this in what we call functional notation. So I want to show you what you're going to see in your book, and I want you to see how we can, until we get to functions, how you can just make a very easy change. So let's read this. It says, Technology is now promising to bring light, fast, and beautiful wheelchairs to millions of people with disabilities. A company is planning to manufacture these radically different wheelchairs. Fixed costs will be $500,000, and then it's going to cost $4,000 to produce each wheelchair. Each wheelchair will be sold for $600 each. How many wheelchairs must be sold before the company breaks even? Start right there. Don't even write anything like an equation yet, because you have to define whatever variable you use in your equation. I need to see what it means. So how many wheelchairs? That's what we want to know. Let W equal the number of wheelchairs sold or made, right? Number of wheelchairs. All right. So now we have to figure out how much is it going to cost the company to make W, which is a number, W wheelchairs. So the cost depends on how many wheelchairs. What does the fixed cost mean in terms of an equation? What's that like? What do we call that? The fixed cost. What is, well, yeah, it's like a down payment. It's what the company has to put out before it even, it's like the cost to get the company going, right? How do I write it? What form does it take in an equation? How would I start this equation if I wanted to write the cost for the company? Mason? It's like a y-intercept, right? It's a constant. It doesn't vary. A fixed cost is exactly what it says, fixed. It doesn't vary. Okay, it's constant. We're used to writing our equations with the slope part first and then the y-intercept, but really in reality we do the starting point, which is 500,000, and then it's 4,000 to produce each one of these wheelchairs. So when you write this expression, what does that expression represent in terms of words? 4,000 times W. First of all, do you know what the units are here for 4,000 times W? What would the units be? Dollars. Because this number is your slope. It's $4,000 for each wheelchair. So the wheelchairs are going to cancel the units. Okay, so this is the amount of money it costs to make how many wheelchairs? How many wheelchairs? W wheelchairs, right? W, because W is the number of wheelchairs. Okay, so that's how much it costs to make them, along with the fixed costs. Voila, we have our cost equation. That's how much it costs to make W wheelchairs. Okay, now what you would see in the book looks like this, because they say the cost depends on the number of wheelchairs. We get that. So they use this kind of notation, C of W. This is functional notation. We haven't covered this yet. So when you see C of W or P of W or X or R of X, just replace it with the letter, the big letter that's there, like C. That's all you have to do. Okay? All right. Now, how much revenue are we going to pull in? How much revenue are we going to pull in when we sell W wheelchairs, Caitlin? Yep. Does anybody have their textbook? Does anybody have their textbook with them? Turn to section 5.1, numbers, example 7. So you see where Mason's coming from. What do you think the wheelchairs are going to cost? Does 600 seem reasonable? No, it's example, not exercise. Yeah, example means it's in the reading. Yeah. Okay, so how much are the wheelchairs selling for?
600.
600. Mm-hmm. So what's the revenue? Let's see. Okay. Yeah. What's the revenue going to be in terms of W? If I sell one wheelchair, how much money do I take in? No. Forget this equation. This is cost. I sell one wheelchair. How much money does my company get? 600. 2 wheelchairs? 3 wheelchairs? So what's the revenue equal to? What's the revenue equal to? 600 times W, right? Okay, so here we have 600 W. What does that define? The amount of the revenue from selling how many wheelchairs? W wheelchairs. All right. So what are we saying where the break-even point is? The break-even point is when these two equal each other, right? When does R equal C? So let's set it up. When does R equal C? When does the revenue finally match the cost? We have 600 W equals 500,000 plus 400 W. So let's solve this for the number of wheelchairs. Let's solve it for W. So what's the first thing I'm going to do here to solve this equation for W? Anybody know? Solve this for, yep, subtract 400 W from both sides. And I get 200 W equals $500,000. Now, is it okay if I just go like this? Boom, 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 boom. What's the matter? Oh, 4,000. Oh, so where's the typo? Did you put your book away? Did you put your book away, Tony? Where's the typo here, folks? Look what I wrote, 400 W. So where's the typo? How much does it cost to make each one? 400. That's my typo. So I apologize for the typo. There we go. It's $400. Go there. I was solving the problem. Look at how I solved it as if it was 400 because I've done this in my brain. So I apologize for my typo. It's 400. So we get 200 W equals 500,000. W equals 500,000 divided by 200. And what does that give me for how many wheelchairs just to break even? 2,500. Okay. When I sell 2,500, I have $0 for cost and revenue. They're equal. Does that make sense? No. What it says is if you subtract these two, they're equal, you would get 0. You'd have $0 profit. At this point, no profit. But once you sell more than 2,500, you start to make a profit. Okay? Now, if you wanted to, you could put this in your calculator just like I did at the end of the last one. When Paul asked that question, you can put both of these equations in and you can find that break-even point. What I'd like you to do right now for the last 10 minutes is I'd like you to work on these modeling problems here. I've given you 3. Pick your favorite, the one you think might give you the most problem, so that I can help you out before you leave. What's Monday? Quiz. You can bring in a little cheat sheet, right? Please take advantage of this. Don't be Joe or Jane macho cool and come in with no notes. You can if you want, but have something to help you, all right? And it's only classes 1 through 4, which means classes from last week and up to Monday's class, all right? This stuff's not on it. Okay, so do you want music while you work or no? Anybody have a problem with music while you're working? I know, is it okay?